we're looking at trying to come up with all the important information on a table. So, concavity information. Say we want to do more than what this question asks. We want to know all the extrema and the inflection points and intervals for concavity and all that kind of stuff. We can get all that from our table, right? So how are we going to do this? Well, we had to differentiate, right? We got to get the first derivative, and if we're looking for inflection points and concavity information, we need the second derivative, and that's where we had got interrupted there at the end of our last period, right? So we had applied the quotient rule, gotten this result, now we just need to simplify. So if we distribute the 6 on the top here, we're going to get what? 18x squared plus 6 minus 36x squared all over the quantity 3x squared plus 1 squared. And then that's going to give us (6 minus 18x squared I could factor out a 6 on the top, and I'm left with 1 minus 3x squared. There's our final answer for the second derivative. Okay, so let's analyze these things. We already did the first derivative, right? We said that the first derivative, there's no value of x that would ever make the bottom 0, right? Because the x is being squared and we're adding 1 to the 3x squared. So the first derivative is nowhere undefined, but it does equal 0 when the numerator is 0 at x equals 0. So there's a critical number. What about our second derivative? Where is our second derivative? It's nowhere undefined again, right? Because the bottom is never 0. What x values would it equal 0 at, though, if I set the top equal to 0 and solve? Square root of 1/3, isn't it, right? If I set the top equal to 0, it's going to equal 0 when 3x squared equals 1, right? Which would be when x squared equals 1/3, which is when x equals plus or minus 1 over the square root of 3, right? Which is just going to be some decimal, some number between 0 and 1, right? We can just approximate it with a decimal maybe. Okay, so now let's make our table. Okay, so there's our table. We said our domain on this one is all reals, isn't it, right? Because we can plug any value in and we're going to get, any value is going to give us a positive output of this polynomial, which gives us the input of our log function. And the only restriction for logs is, remember that logs, the input of a log has to be positive. Okay, so no matter what x we pick, the input for our log function is positive. So all real values of x are good. We had some critical numbers. We had a first derivative critical number at 0, which is where the first derivative equaled 0. And we had some zeros of the second derivative as well. So we had plus 1 over the square root of 3. And I know you're probably thinking, why is he leaving a square root on the bottom? Mathematicians don't really care about that stuff as much as the algebra books claim. Okay, so there's our critical numbers where the second derivative is 0. Okay, now what? What are we going to do? Got to use our table. Got to go to work on our table here. Which row are we going to work in on this table?
So are we looking for minimum and maximum right now?
Say that again, Caleb.
Are we looking for minimum or maximum?
We're looking for everything. Minima, maxima, and inflection points.
So to find if the x0, y prime 0, to find if that's the minimum or maximum, we could take the second derivative to find if it's positive or negative concavity.
Okay, good. So yeah, we're going to work in the second derivative row, aren't we? We want to work as far down the table as we can. So we can apply the second derivative test at 0, couldn't we? Right? Because the second derivative test, remember, is a means for determining whether first derivative zeros are minima or maxima, right? Okay, so we know we've got this 0 of the first derivative, so it's a horizontal tangent line, right? Well, let's evaluate the sign of the second derivative at 0. Okay, here's our second derivative. So we could just do f double prime of 0. What's that going to give us? It's going to give us 6 times 1, right? So we're going to get a positive number on the top and a positive number on the bottom. That's always positive because it's being squared, which means we get a positive second derivative. So what kind of an extremum is that? Type it in chat, please, everybody. What kind of an extremum, a minimum or a maximum, do we have at x equals 0? Yeah, good. It's a minimum, right? And we know that a horizontal tangent line, we have a positive second derivative, gives us a happy function, positive happy function there. So we get a minimum. And then if we want to know, there's really nothing, we could fill in these blanks. This is unnecessary, but because this is a minimum, we don't even have to do the math. We just know that every place to the left of that 0, the function is decreasing, isn't it? Right? Because this is a minimum. The ant's walking downhill towards the minimum and uphill after the minimum, right? We don't even have to add that stuff. It's just implied, but we can. What's the one other thing we need here? Actually, 2 other things we need to determine if we have inflection points. What do we got to do here on our table? We got to work in the second derivative row. What are inflection points again? Type it in chat. What's the definition of an inflection point? Okay, changes in concavity. Places where the sign of the concavity switches, right? And where there is a tangent line, right? We need to know that too, where the function's continuous. But that's not what we're worried about now. So then what do we have to do to determine if those zeros of the second derivative are in fact changes in sign for the concavity? What do we have to do here? Kyle, what do we have to do?
Would you use the first derivative test and see if the signs align?
I mean, we could revert. Well, we can't revert to the first derivative test. I mean, we might be able to, but it's a lot of extra work. If we're just trying to find out if we have points of inflection, we need to be working in the second derivative row to see if those zeros are places where the sign of the second derivative changes. Okay, how am I going to do that? I mean, maybe you were thinking the right thing when you said first derivative test because you're associating that with a test point. I don't know. But what do we have to do to see, like, how could I tell? Look at this value right here, right? At x equals negative 1 over the square root of 3. I have a 0 of the second derivative. How am I going to know if that's a place where the second derivative has a sign change? What do I have to do? What do I have to do, somebody?
Don't you have to take test points from in between above and below those?
Yeah, very good.
Positive or negative?
Excellent. We just need test points, don't we? Yeah, we need test points. So we could pick a value to the left of -1 over the square root of 3, something like, how about -1, right? If I evaluate my second derivative at -1, what am I going to get? I'm going to get 6 times, at -1, x squared is 1. So I'm going to get 1 minus 3. That's negative, right? I get positive times negative on the top, which is negative, divided by positive. That gives me a negative concavity there, doesn't it? Right? So then I know that this is an inflection point because it's a place where we're transitioning from negative second derivative to positive second derivative. So we're going from concave down to concave up, right? Okay, and then same thing over here. We could just pick the point, how about x equals 1, and we're going to get the same result, right? I'll just do this. F double prime of plus or minus 1 is going to give us the same result. We're going to get negative over positive, which is negative. And so this is also an inflection point. So let's use this table then to answer all these questions. We want to know the intervals on which the function is concave up or concave down. Okay, so type in, please, using interval notation. We'll just put a comma between intervals. Type in the intervals where the function is concave down. Just type those in chat. Where is it concave down? Concavity is a second derivative issue, right? So we're just looking in the second derivative row of our table.
I think it might be a little hard to type that.
Yeah, you don't have to, just type the word infinity for the infinity parts. Oh, and then how about this? Okay, yeah, you're right. I see why, because of the square root of 3 part. Let's turn that into a decimal approximation. I get your point. So let's turn that into a decimal, which is it's about 0.558. Let's just say to 2 places it's 0.58. So we've got use those decimal values. Ooh, look at that. Oh my goodness. Creativity. Yeah, good. Okay, excellent. So we've got this interval right here, don't we? Here's a negative interval from negative infinity to negative 1 over the square root of 3, or, comma just means or, that's our shortcut for interval notation. This interval, all values of x greater than 1 over the square root of 3, okay? And we could say that our function is concave up on this interval, right? Between negative and positive 1 over the square root of 3. That interval right there. Okay, and then we see where we have inflection points. Okay. All right, good stuff. And so that's what we get, something like that, right? Doesn't that make sense? We had our minimum at x equals 0, and we had these inflection points, and we can see that's where it's transitioning from concave down to concave up, back to concave down, right? Tangent lines would sit above the curve to the left of that inflection point. They would sit below the curve between the inflection points, and they would sit above the curve again to the right of that right inflection point. Okay? Okay, how about one like this? Let's try some of these transcendental functions, these logs and exponentials and things like that, where we're not just dealing with polynomials all the time. Okay, what about this one? What's the domain? And why? Type it in. What's the domain of that? All reals? Okay, how come, Seth? You're right.
X, well, I mean, there's nothing that would really go wrong. X squared can never be undefined if you put a real into it, and then E is a constant, so E to the negative 2x is E to some power. So then that's never going to be wrong.
Okay, that's a good way of thinking about it. Nothing bad can happen, right? If we're plugging, there's no value of x we could ever plug in here that's going to cause something to be undefined, right? Another way we could maybe look at this real briefly, let's think about what let's look at this function, e to the minus 2x, for just a second. This is a good opportunity for a little bit of review. So if we take the function y equals e to the x, remember what that looks like, right? That's just going to be that function. Agreed? Okay, so what if I multiply the x by 2? What's that doing? Well, if I multiply the x by 2, it's just, all that's going to do is make the exponents bigger faster, right? If I plug in an x value, I'm going to double that exponent. So it's just going to make this thing steeper. Just going to be the same shape, but it's just going to be slightly steeper, right? Doesn't change things a ton, though. Well, what if I plug in a negative there? Think what this means in terms of transformations, right? Let me just make this a 2x too. Anytime that I multiply, and e to the negative 2x is the same thing as e to the 2 times negative x, right? Aren't I effectively just multiplying the input value by negative 1 there? Would everybody agree? Right? That's the same thing as saying e to the 2 times negative x. So I'm just replacing the x with a negative x, multiplying the x by negative 1. Same thing, right? What does that do in terms of a transformation? If I multiply a function by a negative, it reflects it over the x-axis. Andy, what's it do if I multiply the input value x by a negative 1?
It's the same thing as like 1 over x to the 1.
Well, true, but what's it do to the graph is what I want to know.
Is it like, as it gets larger, as the x gets larger, does it get way smaller or something?
It does. Okay, but I just want to know in general, what's it do? Like if I've got some function f of x and g of x equals f of negative x, if I multiply the input by negative 1, what's that doing?
So does it like asymptote out at the y equals 0?
No, but can't you control your dog?
No, I can't.
Anybody else want to weigh in on that? What's it do? Going back to honors algebra 2, what did we say about that? It reflects it over the y-axis is all it does. Okay? We don't use that reflection very often, but that's a good one to be reminded of, right? This is a reflection. When we do something like this, that's reflection over the y-axis, whereas if we do something like this instead, if we have a parent function f of x and h of x is negative f of x, well, that's just a regular old reflection over the x-axis, right? So all this is doing then, when we put a negative out here, you had the right description of what it was doing, Andy, but it just, maybe you didn't understand my question. I don't know, but I just wanted to know, without specifically talking about an exponential graph, that just reflects it over the y-axis, which does what you said. I mean, it's just going to tail off to the right. So that's what we get with an exponential function with a negative exponent. Okay, that makes sense. Maybe give me a 1 to 5 on that transformation stuff, on that reflection. Does that everybody get that? That makes sense. If I'm just going to replace an input variable with its opposite, then that always serves to reflect it over the y-axis. Okay, so then going back to Seth's observation earlier, yeah, this is going to be fine, isn't it? There's no value. If I look at this exponential function that we just created, yeah, the domain is all reals, isn't it? Right? So if the domain is all reals for the exponential function, and it's obviously all reals for x squared and plus 5, then we got no problems, right? So the domain is all reals. Okay? Any symmetry here? What do you think? We probably have to run the test, don't we? Test for symmetry. So let's see what happens. Our test for symmetry is just to evaluate our function at negative x and see what happens. So what is f of negative x here? Let's see what we get. That's going to give us negative x squared is the same as x squared, but then I'm getting e to the negative 2 times negative x. I'm getting e to the 2x plus 5. Okay, that's not, everybody agree? That's neither f of x nor negative f of x, right? So there's no symmetry here. That is not equal to f of x, and it's not equal to the opposite of f of x. So we've got no symmetry. Okay? That would have helped. That always helps. We can fill in some blanks for free then in our table, but we're stuck. All right, so we got to do some calculus. We got to take some derivatives. First derivative. What's our first derivative going to be here? Miss House, help us out.
Do you have to use the product rule or no?
We do, don't we? We got a product of x squared times e to the negative 2x.
So x squared times negative 2xe. I don't actually know.
Okay, so remember the derivative, let's remind ourselves about this one. The derivative,
Wasn't just the same?
yeah, it is. The derivative with respect to x of e to the u is just e to the u times u prime, right?
So e to the negative 2x times negative 2.
There you go. So negative 2 e to the negative 2x. Good. Plus e to the negative 2x times
Yeah.
2x. Good. Okay. So we could clean that up a little bit, couldn't we? We could factor out, it looks like how about if we factor out a 2x e to the negative 2x? And that leaves us with 1, right, from over here, minus, we got a negative there, minus x. Everybody buy that? Does that make sense? Give me 1 to 5 on that. Okay, so we got it factored. That's good. So let's talk about critical numbers for the first derivative. Are there any places where the first derivative is undefined? Yes or no? That's right. No. How come? Because there's no place that causes any problems, right? If I've got a product, look at all these factors that I've got. I'm multiplying here. I've got 2x times this factor times this factor. None of those individual factors have any problems, so why would their product, right? 2x is defined everywhere. E to the negative 2x is defined everywhere, like we previously discussed, and 1 minus x is defined everywhere. So we can say with confidence that f prime is nowhere undefined. Okay, Daisy, where does our derivative equal 0?
At 1.
At 1? Anyplace else?
Not sure.
How about that factor right there? Right, if I were to set my derivative equal to 0, think what I just did there. I set 2x times, I'm gonna divide it into a bunch of factors. By the zero product property, right, the product of that factor times that factor times that factor would equal 0 when that one equals 0. That's right. Sorry, that one equals, x equals 1, which is when that factor equals 0. Any others? Well, we know this one never equals 0, does it? If we look back at the previous page, this e to the negative 2x is asymptotic. It never gets down to 0. So that one never gives us a 0. But when does 2x equal 0? When x equals what? Okay, you said 0, right? Yeah, good. So we're getting 2 results here. Either x equals 1 or x equals 0. Okay? All right, so let's move on. Let's take a second derivative. So how do we want to do this? Let's go ahead. I mean, honestly, I would probably just differentiate this top one up here instead of having to do all these products, right? So why don't we, it's not a huge crime if you don't differentiate that first row, but I think that's what I would do. I'm going to rewrite this here as negative 2 x squared e to the negative 2x plus 2x e to the negative 2x. Now look at this. We can kind of cheat a little bit here, can't we? Because we've already done this derivative. up here, didn't we? Isn't the derivative of f of x the very same thing as that derivative right there? Because the derivative of 5 is 0. Everybody see that? So we already did all the work, right? We already did all the work of differentiating that part in the, whatever that is, magenta box there, right? So when we differentiate now, we already know that I'm going to get -2 times the derivative of that, which is all that stuff right up there, okay? Which is a -2, I'll just kind of clean this up, -2x squared e to the minus 2x plus 2x e to the minus 2x. Plus, now I've got to differentiate that part right there, don't I? Okay. So we'll just do the same thing that we did the first time. We're going to use the product rule, aren't we? So we're going to get 2x times the derivative of e to the negative 2x, which was just that stuff right there. We already did that work, didn't we? We'll recycle it here. Plus e to the negative 2x times the derivative of 2x, which is 2. Okay, so there's our second derivative. Let's clean this up here. So if I distribute my -2, I'm going to get a 4x squared e to the negative 2x minus 4x e to the negative 2x minus 4x e to the negative 2x plus 2 e to the negative 2x. And I could combine, these are like terms, aren't they? I could combine those. So I get 4x squared e to the negative 2x minus 8x e to the negative 2x plus 2 e to the negative 2x. And now I could factor out a 2 e to the negative 2x. And what's left behind? So I'm getting 2x squared right, minus 4x plus 1. It's a lot of work, right? But we got it whittled down to something we can deal with now. So second derivative, where are the zeros of the second derivative? Well, we know that this first factor is never equal to 0, but maybe we could find zeros of this one, right? So we know second derivative equals 0 when we solve that, we get solutions to this quadratic equation, when this quadratic expression 2x squared minus 4x plus 1 equals 0. Okay, does that have real solutions, first of all? Yes or no? Does that have real solutions?
No.
How come?
I mean, you could put it into the quadratic function that I forgot the determinant or whatever.
Discriminant?
So, yeah, if you do the first step to the first bottoms up method, you'll get x squared minus 4x plus 2, and there's no numbers that can ever add to -4 and multiply to 2.
Okay.
You're just done right there.
Okay, right. But all that's telling us is it doesn't factor conveniently, right? Just because bottoms up doesn't work, because this thing doesn't factor conveniently, doesn't mean it doesn't have real zeros, right? So we should just be able to evaluate the sign of the discriminant here. What's the sign? Let's just look at b squared minus 4ac for a second. This is a really, and this is, this is great prep for you guys, like for SATs and things too, because it's ACTs and SAT, because there's so much of this kind of stuff on there, right? So the discriminant, b squared minus 4ac, is that going to be positive or negative or 0 on this? Well, b squared is 16, right? Minus 4 times 2 times 1. Well, that's positive. So we do get 2 real solutions on this, don't we? So then we have to go through the hassle of probably using the quadratic. We're either going to complete the square or use the quadratic formula on this one, right? Take your pick. Probably quadratic formula, I guess. I mean, they're about the same, but if we use the quadratic formula, what are we going to get here then? X equals negative b, so positive 4, plus or minus the square root of the discriminant. So 16 minus 4 times 2 times 1, all divided by 2a, so 4. So we're getting 4 over 4 is 1, plus or minus the square root of 8 over 4. So that's 2 radical 2 over 4 would be the square root of 2 over 2, right? So we do get 2 critical numbers then. We know that the second derivative equals 0 at these 2 places. I mean, I shouldn't call them critical numbers. Those are zeros of the second derivative that we'll put into our table, right? Okay, well, true to form in calculus, we got through about a problem and a half in an entire period. So we'll just pick this one up next time. So where this is going to go from here, you can finish up. I extended the deadline a little bit on that, on the last concavity assignment. But honestly, our next section is just more of the same. We're just going to look at we're going to really hit these tables hard. So I'm going to give you another assignment or 2 on just doing more tables with some different kinds of functions. And for the next several times we meet, we're just going to keep cranking through this stuff so you can see some examples and kind of absorb how you think about this stuff and then practice on your own. Okay, have a great day. I'm here after school. I will see you. If I don't see you then, I'll see you on Friday.